So we have come to the end of chapter 5. We're going to look at section 5.7, and all of our knowledge that we have gained thus far when discussing the concept of linear equations really does culminate nicely into this section. Section 5.7 is about statistics, scatter plots, and something called lines of fit. Our vocabulary today has to do with a lot of statistical information. And so when we have a scatter plot, it's kind of like an XY axis having bits of information on it. For example, I've made this scatter plot, and it's just a matching of some students that I've had in the past that, I'm making this up by the way, some students that I had in the past, and this is their height versus weight. So I had some short students who were really light, and I had one kind of tall student, tall student that was kind of light, but for the most part, as the height of my students increases, so does their weight, which kind of makes a logical sense. And so I have a scatter plot here, which is a relationship, which is basically data represented on a chart with two or more variables, generally two variables. So we might say each point represents a data point, or like in this case, a person. All right. So each point represents a person. And so what I might have when I look at my scatter plot is I may have something called a positive correlation. A positive correlation means as one variable increases, so does the other. If you look at this, you will see that we indeed have a positive correlation here. So a positive correlation just means that in general, the information is increasing. It looks like a positive slope. Right? Positive correlation says if I looked at all the data, it would look kind of like it's moving up. It would have like a positive slope energy to it. Okay. Let's take a look at this scatter plot here. This looks really sloppily written, my bad, but basically right here I have students, the minutes a student is late to class. So the more minutes, the greater the amount of minutes a student is generally late to class, is being mapped with their score on the test. So I've got one kid that just, doesn't come. And so when he doesn't come to class half the time, where he's so late, he's like 1 minute before the bell. I've got a situation where this kid isn't doing very well in my class, so his score on the last test was low. Obviously, I'm making this up, guys. However, the relationship here, the fewer minutes you are late to class, the better your score is on this imaginary fictitious classroom situation, would be a negative correlation, right? So the negative correlation is that it goes down to the right. It's a lot like a slope that's negative, right? It's a lot like a slope that's negative. So negative correlation is where your information as one variable increases, the other one decreases. So as the minutes late to class increase, the score on test decreases. Or if you could look at it kind of differently, as your score on test increases, your minutes late to class have to decrease for the higher score, something like that. All right. So that's a positive correlation, and that was a positive correlation here. This is a negative correlation. And line of fit. So basically, and I've kind of drawn these things in here, these two lines that I've drawn here and here. I guess I should put the arrows on both sides. These are kind of like lines of fit. So basically what it is it's a line that I'm going to use to approximate my data. Now it's not perfectly linear, but I'm saying, all right, well, you know what? This is like the trend. I'm trying to show an approximate trend of what's going on. And in mathematics, oftentimes the calculators you have, even with Desmos, I'm sure I've done it before, but I can't do it right now, but I'll try to see if I can do it for you guys at some time. With Desmos, online calculators, graphing calculators and stuff like that, you can put in data, it'll scatter plot it for you, and you can come up with a best fit line. So a line of fit is what you're eyeballing, you're approximating. A best fit line takes some calculations into consideration, and oftentimes, or at least for us right now, we will allow some digital devices to do that for us. You can do that with your calculator, or you can do that, again, as I said, with an online program like Desmos. And the idea of linear interpolation is very similar to another phrase that we learned in a previous lesson. We did linear, do you remember extrapolation? And honestly, sometimes I have to remind myself of the difference between the two. But linear extrapolation says I'm going to take information. This is me reviewing the last definition we had, linear extrapolation, thought bubble here, is when we have information and we're going to predict what's happening kind of outside the data that we have. And linear interpolation is going to be trying to predict what's going on inside the data we have. So, for instance, let's say this was the height of a student, right? Height of students based on the height of students and their weight. And what if I had a student that was, I don't know, I'm not doing good. Let's say 5 foot, I don't know, let's say 5'11", 5'11" inches. And let's say 5'11" inches was somewhere here with, I don't know, 6'2" here or something. I'm just making stuff up, people, but you get me. And over here, I've got one of my shorter students at 4 foot 3 inches. All right. Let's say this was my situation, and I wanted to figure out, well, what is the approximate weight given my class data of a student who is 5'11". I would see that I don't have a student that's 5'11". But what I can do, like there's nobody that fell on that particular part of my graph, but what I could do is use my line here of fit, or line of best fit, and do some linear interpolation. I can kind of see what's going on given the data inside my data. This looks like it might be, and I can use that to figure out whatever the heights are the weights are over here, let's say 175 pounds or something like that. And I can say, oh, well, that a 5'11" kid might be approximately 175 pounds according to my data. And I can use that. So that's what linear interpolation is. Let's get to some real examples so we can have more math fun. So as usual, your textbook has really nice graphics, and they're showing a positive slope, which is a positive correlation. A negative slope is that negative correlation. And sometimes you can't really see any relationship at all, where you just like, it's no real correlation. Those two variables are not correlating. They're not showing any kind of relationship with one another. So here in example 1, we're just going to practice analyzing a scatter plot. And so one thing that's really important to do is when you see a graph, you really want to make sure you understand what they are talking about. So I'm going to look over here and we see that fat grams and calories in fast food choices. So just looking as the fat grams increase, does it look like the calories are increasing? And so you want to kind of just eyeball it and see if you see any kind of correlation. Is there a positive correlation, a negative correlation, or no correlation? So the graph shows that fat grams and calories for selected choices at fast food restaurants. And as I look at this, I do see a positive correlation, because it seems like even though it's, the lower we are, the lower it is in calories, and the higher we go in terms of fat grams, the greater amount of calories. So I'm going to say that this is a positive correlation. Part B, we're looking at the graph shows the weight and the highway gas mileage of a selected cars. So it looks like the cars that are pretty light have a higher gas mileage. They seem to be able to be more efficient, and that seems to be the trend. As the weight increases, it seems like there is a decrease in gas mileage. So this relationship seems like it has a negative correlation. There seems to be a negative slope to the data there. Let's go on. So looking at example 2, we're going to find a line of fit. Okay, so first here with this, we're going to draw a scatter plot and determine the relationship exists, if any. And so basically, as we've talked about before, we're going to use the first value as our x and the second as our y. And we're going to plot these values. And after we plot the value, we're going to try to draw a line of fit. Let's check that out. So the data is plotted here, and I kind of stole this a little bit from the textbook. And so, but basically the data is plotted here. Each of these points are best plotted here. And so that's all you needed to do for part A. For part B, you're going to draw a line of fit for the scatter plot. So basically what you're going to do is try to draw a line, and the text did this one for us, that hits or comes close to as many points as possible. And that happens here. You've got this line of fit. So that's 2 things done here. And the final thing we'll do together, we're going to write the slope-intercept form of the equation for the line of fit. So in order to write a slope-intercept form, we remember slope-intercept, right? Slope-intercept was one of our favorite points, right? We would do a little, it was y equals mx plus b. And so we knew how to do that given some points. So basically what we're going to do is use a couple of the points. It looks like this line goes through these 3 points here. And so I could use 2 points to determine a line. So I'm going to use these 2 on either side. So the points that I'm going to use would be 5 and 3,000. And the other point I'll use is 9 and what's that? 9 and 4,500. All right, so with that, all I need to do is the thing that I've been doing for a long time in this chapter, which is finding the slope of the line, then I find the y-intercept, then I've got the equation. So the slope is going to be change in y over change in x. So that's 4,500 subtracting 3,000, sorry about that. All of that over 9 minus 5. And so I get a 4 in the denominator, and at the top, let me write this a little bit better. In the numerator, I get 1,500. There we go. And in the denominator, I get 4. And I can reduce that. I can reduce that to 4 goes into 1,500, 3 with a remainder of 3. 4 goes into 37 times with a remainder to 375. So my slope is 375. So far I can say y is equal to 375x plus b, and now I need to figure out what that b is. Remember, I got to find that out, and I can use any point that I've been using to solve this. So since the 2 points I've used were 5 and 3,000 or 9 and 4,500, I've got to use one of these points because it's a part of the line, right? And so I'm going to use the 5 and 3,000. So 3,000 is equal to 375 times 5 plus b. And that's going to leave me with 3,000 is equal to, let me do some quick math, left with 1,875. And then I'm going to solve for b by subtracting 1,875 from 3,000. So I'm getting that b is equal to 1,125. And now that I've got b and I have m, I'm going to say y is equal to my slope, 375, x plus 1,125 as my y-intercept. And I'm going to box it because that's my final answer. And I'll take the box off of this guy because he is not my final answer. Make sense? I hope so. All right, let's take a look at linear interpolation. So here in example 2, we're going to go back to example 1 and we're going to use the equation for the line of fit to estimate the number of bald eagle pairs in 1998. So I'm going to grab my equation really quickly because I'm going to definitely need that. So y is equal to 375x plus 1,125. And now I need to really be careful. What does X stand for? X stands for the years since 1985. And I'm trying to figure out what's going on with the year 1998. So how many years have transpired since 1985 to 1998? That's what I need to calculate right now. And if you and I are thinking the same thing, it looks like 13 years. And if you look up here, there really is no data for 13 years. So we're doing a little linear extrapolation. We're saying, all right, approximately this might be the case, given the fact that what we see is the trend over time, that kind of spanned over that time. So 1998, for our intents and purposes, refers to the 13th year. Refers to 13, right? Let's go back up. Remember, this is years since 1985. If you take 1985 and add 13, you'll get 1998. So that would be 13 on that graph. So we're going to do exactly what you think. We're going to plug 13 into the equation. 375 times 13 plus 1,125. We'll do our multiplication here. We get that y is now equal to 4,875 plus 1,125, and then when we do that, we add it together, and let me see, adding that together right now as we speak, we get 6,000 even. So the thought is that the prediction is that the number of bald eagle pairs that we'd have would be 6,000 according to our data. All right, now that's all we have for this chapter, for this section and chapter. Please let me know if there's any way that I can help you. I look forward to talking to you. Please, please take care.